The roads are made with some curves which are designed with a bank in them. In other words, the curves are not flat. They have a certain degree of angle designed into the road. This allows you to traverse that curve at a higher speed than if it were flat.
ਵਿਦਿਆਰਥੀਓ, ਤੁਹਾਡਾ ਅੱਜ ਦੀ ਕਲਾਸ ਬੈਂਕਿੰਗ ਆਫ ਰੋਡਸ ਐਂਡ ਬੈਂਡਿੰਗ ਆਫ ਸਾਈਕਲਿਸਟਸ ਵਿੱਚ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਬੈਂਕਿੰਗ ਆਫ ਰੋਡਸ ਅਤੇ ਬੈਂਡਿੰਗ ਆਫ ਸਾਈਕਲਿਸਟ ਵਜੋਂ ਇਹਨਾਂ ਦੀ ਸਾਡੇ ਰੋਜ਼ਾਨਾ ਜੀਵਨ ਵਿੱਚ ਵਰਤੋਂ ਬਾਰੇ ਵਿਚਾਰ ਕਰਾਂਗੇ। ਪਰ ਇਸ ਵਿਸ਼ੇ ਤੇ ਵਿਸਥਾਰ ਨਾਲ ਵਿਚਾਰ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਮੈਂ ਤੁਹਾਡੇ ਨਾਲ ਅੱਜ ਦੀ ਕਲਾਸ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਸਾਂਝੇ ਕਰ ਲਵਾਂ।
On completion of this topic, learners will be able to define centrifugal force, describe application of centrifugal force in real life, describe a circular turn of vehicles on level roads, derive mathematical expression on banking of tracks, derive mathematical expression on bending of cyclist.
ਤੁਸੀਂ ਪਹਿਲਾਂ ਯੂਨੀਫਾਰਮ ਸਰਕੂਲਰ ਮੋਸ਼ਨ ਅਤੇ ਇਸ ਤਰ੍ਹਾਂ ਦੇ ਮੋਸ਼ਨ ਲਈ ਰਿਕੁਆਇਰਡ ਫੋਰਸਸ ਬਾਰੇ ਪੜ੍ਹ ਚੁੱਕੇ ਹੋ। ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਤੁਸੀਂ ਸਰਕੂਲਰ ਮੋਸ਼ਨ ਦੇ ਸਪੈਸ਼ਲ ਕੇਸਿਸ, ਬੈਂਕਿੰਗ ਆਫ ਰੋਡਸ ਅਤੇ ਬੈਂਡਿੰਗ ਆਫ ਸਾਈਕਲਿਸਟ ਬਾਰੇ ਪੜ੍ਹਨ ਜਾ ਰਹੇ ਹੋ। ਪਹਿਲਾਂ ਮੈਂ ਇੱਕ ਨਵੀਂ ਟਰਮ ਇੰਟਰੋਡਿਊਸ ਕਰਨਾ ਚਾਹਾਂਗੀ, ਉਹ ਹੈ centrifugal force. You must have often observed that children sitting in a merry-go-round experience outward force as the merry-go-round moves along the circular path. This outward radial force experienced by an object when in circular motion is called centrifugal force. We have experienced that when a bus moves along a circular path and its velocity changes along the radius towards the center of the circular path due to inertia, the passengers experience a force along the radius, but away from the center. This force, called the centrifugal force, is due to the inertial property of the material of bodies. Also, when we are in a car and take a bend, we feel a force pushing us to the outside of the curve. To know more about this force, let us watch this video carefully.
ਮੰਨ ਲਓ ਕਿ ਤੁਸੀਂ ਕਾਰ ਚਲਾ ਰਹੇ ਹੋ। ਡੈਸ਼ਬੋਰਡ ਉੱਤੇ ਸਟੀਅਰਿੰਗ ਦੇ ਦੂਜੇ ਪਾਸੇ ਇੱਕ ਕੈਸਟ ਪਈ ਹੈ। ਜੇ ਤੁਸੀਂ ਸੜਕ ਤੇ ਮੋੜ ਦੇ ਨਾਲ ਹੀ ਕਾਰ ਵੀ ਮੋੜਦੇ ਹੋ ਤਾਂ ਕੈਸਟ ਹਿਲਦੀ ਹੈ ਅਤੇ ਸਟੀਅਰਿੰਗ ਵਾਲੇ ਪਾਸੇ ਚਲੀ ਜਾਂਦੀ ਹੈ। ਇਹ ਸੈਂਟਰੀਪੀਟਲ ਫੋਰਸ ਦੀ ਗੈਰ ਮੌਜੂਦਗੀ ਦੇ ਕਾਰਨ ਹੋਇਆ ਹੈ ਅਤੇ ਇੱਥੇ ਸੈਂਟਰੀਫਿਊਗਲ ਫੋਰਸ ਕੰਮ ਕਰ ਰਹੀ ਹੈ।
The magnitude of the centrifugal force acting on a body of mass m moving with a velocity v along a circular path of radius r is same as that of the centripetal force required to move the body along the circular path. Thus, the centrifugal force acting on the body is F equal to mv square upon r as equation 1. Since the linear velocity of the object moving in circular path is v equal to r omega. Substituting the value of v equal to r omega in equation 1, we get F is equal to m omega square r square upon r, which is equal to m omega square r. Let this be equation 2. As the angular velocity of the object is omega is equal to 2 pi by capital T, which is equal to 2 pi nu, where nu is the frequency of the revolution of the body. On substituting this value of omega in equation 2, we get F is equal to 4 pi square nu square mr, which is the expression for centrifugal force. After all that explanation, let me tell you that the centrifugal force is not a real force. It is purely a pseudo or fictitious force. I know you understand fictitious means fake or false. Scientists have been able to apply the concept of centrifugal force to the advantage of our lives in a lot many situations. This is done by making use of a piece of equipment called a centrifuge. Let me tell you what is a centrifuge. It is generally a device driven by an electric motor that puts an object in rotation around a fixed axis. It is based upon sedimentation principle where the centripetal acceleration makes heavier particles to move outward radially, that is, towards the bottom of the container. In the same manner, lighter objects tend to move to the top. Let me show you a homemade centrifuge.
ਮੰਨ ਲਓ ਕਿ ਇੱਕ ਬਾਲਟੀ ਦੇ ਨਾਲ ਰੱਸੀ ਬੱਝੀ ਹੈ। ਇਸ ਬਾਲਟੀ ਦੇ ਵਿੱਚ ਪਾਣੀ ਅਤੇ ਗਾਰੇ ਦੇ ਮਿਸ਼ਰਣ ਵਾਲਾ ਦੂਸ਼ਿਤ ਪਾਣੀ ਹੈ। ਜਦੋਂ ਬਾਲਟੀ ਘੁੰਮਣਾ ਸ਼ੁਰੂ ਕਰਦੀ ਹੈ ਤਾਂ ਬਾਲਟੀ ਰੋਟੇਸ਼ਨ ਦੇ ਦੌਰਾਨ ਸੈਂਟਰੀਫਿਊਗਲ ਫੋਰਸ ਦੇ ਕਾਰਨ ਰੋਟੇਸ਼ਨ ਦੇ ਐਕਸਿਸ ਤੋਂ ਦੂਰ ਜਾਣ ਦੀ ਕੋਸ਼ਿਸ਼ ਕਰਦੀ ਹੈ। ਕੁਝ ਦੇਰ ਰੋਟੇਟ ਕਰਨ ਤੋਂ ਬਾਅਦ ਜਦੋਂ ਬਾਲਟੀ ਨੂੰ ਰੈਸਟਿੰਗ ਪੋਜੀਸ਼ਨ ਵਿੱਚ ਵਾਪਸ ਲਿਆਂਦਾ ਜਾਂਦਾ ਹੈ ਤਾਂ ਅਸੀਂ ਵੇਖਦੇ ਹਾਂ ਕਿ ਪਾਣੀ ਅਤੇ ਗਾਰਾ ਅੱਡੋ-ਅੱਡ ਹੋ ਗਏ ਹਨ।
Based on the concept of centrifugal force, cream is separated from the milk in cream separators. Wet clothes are dried by dry cleaners in the drying machines. Centrifuges are used to separate honey from the wax, and so on. The list is too long to be completed here. To understand how the concept of centrifugal force works in the given objects, watch here carefully.
ਮੰਨ ਲਓ ਕਿ ਇੱਕ ਬਰਤਨ ਦੁੱਧ ਨਾਲ ਭਰਿਆ ਹੈ। ਇਸ ਬਰਤਨ ਦੇ ਉੱਪਰ ਇੱਕ ਸੈਂਟਰੀਫਿਊਜ ਲਾਇਆ ਜਾਂਦਾ ਹੈ। ਮੋਟਰ ਦੀ ਮਦਦ ਨਾਲ ਸੈਂਟਰੀਫਿਊਜ ਨੂੰ ਰੋਟੇਟ ਕੀਤਾ ਜਾਂਦਾ ਹੈ। ਕੁਝ ਸਮੇਂ ਬਾਅਦ ਮੱਖਣ ਦੁੱਧ ਉੱਪਰ ਤੈਰਨ ਲੱਗ ਜਾਂਦਾ ਹੈ ਕਿਉਂਕਿ ਇਹ ਦੁੱਧ ਨਾਲੋਂ ਹਲਕਾ ਹੁੰਦਾ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਮੱਖਣ ਦੁੱਧ ਤੋਂ ਅਲੱਗ ਹੋ ਗਿਆ। ਇੱਕ ਹੋਰ ਉਦਾਹਰਣ ਵੇਖੋ। ਇੱਕ ਹਾਈ ਸਪੀਡ ਸੈਂਟਰੀਫਿਊਜ ਹੈ ਜਿਸ ਵਿੱਚ 4 ਟੈਸਟ ਟਿਊਬਾਂ ਰੱਖੀਆਂ ਗਈਆਂ ਹਨ। ਇੱਕ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ ਸਿਆਹੀ ਯਾਨੀ ਇੰਕ ਰੱਖੀ ਗਈ ਹੈ ਜਦੋਂ ਕਿ ਬਾਕੀ ਦੀਆਂ 3 ਟੈਸਟ ਟਿਊਬਾਂ ਵਿੱਚ ਬਲੱਡ, ਗੰਦਾ ਪਾਣੀ ਅਤੇ ਕੈਲਸ਼ੀਅਮ ਸਲਫੇਟ ਦਾ ਸੋਲਿਊਸ਼ਨ ਹੈ। ਸੈਂਟਰੀਫਿਊਜ ਨੂੰ ਟਾਈਟਲੀ ਬੰਦ ਕਰਨ ਤੋਂ ਬਾਅਦ ਇਸ ਨੂੰ ਰੋਟੇਟ ਕਰਨਾ ਸ਼ੁਰੂ ਕੀਤਾ ਗਿਆ ਹੈ। ਹਾਈ ਸਪੀਡ ਰੋਟੇਸ਼ਨ ਦੇ ਬਾਅਦ ਜਦੋਂ ਸੈਂਟਰੀਫਿਊਜ ਨੂੰ ਰੈਸਟ ਪੋਜੀਸ਼ਨ ਵਿੱਚ ਵਾਪਸ ਲਿਆਇਆ ਜਾਂਦਾ ਹੈ ਤਾਂ ਇੰਕ ਵਾਲੀ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ ਡਾਈ ਅਤੇ ਸੋਲਵੈਂਟ ਸੈਪਰੇਟ ਹੋ ਗਏ ਹਨ। ਬਲੱਡ ਵਾਲੀ ਟਿਊਬ ਵਿੱਚ ਪਲਾਜ਼ਮਾ ਅਤੇ ਬਲੱਡ ਸੈਲਸ ਸੈਪਰੇਟ ਹੋ ਗਏ। ਇਸੇ ਤਰ੍ਹਾਂ ਗੰਦੇ ਪਾਣੀ ਵਾਲੀ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ ਗਾਰਾ ਅਤੇ ਪਾਣੀ ਅਤੇ ਕੈਲਸ਼ੀਅਮ ਸਲਫੇਟ ਦੇ ਸੋਲਿਊਸ਼ਨ ਵਾਲੀ ਟੈਸਟ ਟਿਊਬ ਵਿੱਚ ਕੈਲਸ਼ੀਅਮ ਸਲਫੇਟ ਦਾ ਪ੍ਰੈਸਿਪੀਟੇਟ ਅਤੇ ਸੋਲਿਊਸ਼ਨ ਸੈਪਰੇਟ ਹੋ ਗਏ ਹਨ। ਇਹਨਾਂ ਸਭ ਦਾ ਕਾਰਨ ਸੈਂਟਰੀਫਿਊਗਲ ਫੋਰਸ ਹੈ।
A mass m of the dense liquid revolving at a distance r from the axis of rotation of the centrifuge requires a centripetal force F equal to m omega square r, where omega is the angular speed of the centrifuge. The required centripetal force is provided to this mass of the liquid by the pressure gradient existing in the liquid. If, in place of this mass of the liquid, lighter particles of mass m dash, in other words, m dash less than m, are present, then the centripetal force F is equal to m omega square r, on the dense liquid will be greater than the centripetal force F dash equal to m dash omega square r on the lighter particles. As a result, the lighter particles move towards the axis of rotation under the effect of the net force F minus F dash equal to m omega square r minus m dash omega square r. On simplification, we get the net force F net equal to omega square r into whole of m minus m dash. This explains why is it that the heavy particles are found to settle down while the lighter ones float after centrifugation. A discussion of centrifugal force was required to give you an insight into the concept of objects moving in circular motions. Not only objects, we all experience motion along a curved path in our daily life. Well, this motion may not be an exact circular motion. However, we can think of curved path as a sequence of circular motions of different radii. Consider the experience of a car drive which undergoes a sharp turn.
ਇੱਕ ਵਿਅਕਤੀ ਕਾਰ ਦੀ ਪਿਛਲੀ ਸੀਟ ਤੇ ਬੈਠਾ ਹੈ ਅਤੇ ਉਹ ਕਾਰ ਦੇ ਮੋਸ਼ਨ ਦੇ ਨਾਲ ਮੂਵ ਕਰ ਰਿਹਾ ਹੈ। ਜੇ ਵਿਅਕਤੀ ਕਾਰ ਦੇ ਸੈਂਟਰ ਆਫ ਮੋਸ਼ਨ ਤੋਂ ਦੂਰ ਕਾਰ ਦੀ ਫਾਰਦਰ ਸਾਈਡ ਤੇ ਹੈ ਅਤੇ ਕਾਰ ਦੀ ਸਾਈਡ ਨਾਲ ਲੱਗ ਕੇ ਬੈਠਾ ਹੈ ਤਾਂ ਉਹ ਕਾਰ ਦੇ ਮੋਸ਼ਨ ਦਾ ਹਿੱਸਾ ਬਣ ਜਾਂਦਾ ਹੈ। ਹੁਣ ਕਾਰ ਦੀ ਸਾਈਡ ਨਾਰਮਲ ਫੋਰਸ ਅਪਲਾਈ ਕਰਕੇ ਵਿਅਕਤੀ ਦੇ ਸਰਕੂਲਰ ਮੋਸ਼ਨ ਲਈ ਸੈਂਟਰੀਪੀਟਲ ਫੋਰਸ ਦੀ ਜ਼ਰੂਰਤ ਨੂੰ ਪੂਰਾ ਕਰਦੀ ਹੈ।
Now, let us concentrate on what is done to turn a car to negotiate a sharp turn.
Consider a car of weight mg going around on a circular turn of radius r with velocity v on a level road. The body of the car tends to move straight in accordance with its natural tendency. Now, as wheel is made to move sideways due to the change in direction, the wheel has the tendency to have relative motion with respect to the road in the direction away from the center of path.
Thus, while taking the round, the tires of the vehicles try to leave the road and go away from the center of the curve. In turn, the road applies friction which is directed towards the center. Due to this, the forces of friction F1 and F2 act inward at the inner and the outer tires respectively. Thus, if R1 and R2 are the normal reactions of the ground on the inner and outer tires respectively, then F1 is equal to mu R1 and F2 is equal to mu R2 as equation 1, where mu is the coefficient of friction between the tires and the road. The total force of friction provides the necessary centripetal force. In other words, F1 plus F2 is equal to mv square by r. Let this be equation number 2. Using equation 1 in equation 2, we get mu r1 plus mu r2 equal to mv square upon r. Simplifying this, we get mu into whole of r1 plus r2 equal to mv square upon r as equation 3. As there can be no motion of the car along vertical, the total normal reaction on the car balances its weight. Thus, R is equal to mg. We have R1 plus R2 is equal to mg. Let this be equation number 4. Using equation 4 in equation 3, we get mu mg is equal to mv square upon r. On simplifying, we get mu equal to v square by rg representing equation 5. On simplifying again, we get V is equal to under root mu rg, representing equation 6. The equation 6 gives the maximum velocity with which the car can take a circular turn of radius r without skidding when the coefficient of friction between the tires and the road is mu. A study of this equation explains that if friction between tires and the road is more, then we can negotiate a curved path with higher speed and vice versa. It also explains why we drive slowly on slippery roads and more so why sharper turns having smaller radius of curvature is negotiated with a smaller speed. ਤੁਸੀਂ ਸਾਰੇ ਹੀ ਜਾਣਦੇ ਹੋ ਕਿ ਇੱਕ ਵਾਹਨ ਇੱਕ ਨਿਰਧਾਰਿਤ ਸਪੀਡ ਤੇ ਕਰਵਡ ਟਰੈਕ ਵਿੱਚ ਬਿਨਾਂ ਫਿਸਲੇ ਚੱਲ ਸਕਦਾ ਹੈ। ਇਸ ਦੇ ਲਈ ਢੁਕਵੀਂ ਸੈਂਟਰੀਪੀਟਲ ਫੋਰਸ ਦੀ ਜ਼ਰੂਰਤ ਹੈ ਜੋ ਕਿ ਟਰੈਕ ਦੇ ਬਾਹਰੀ ਐਜ ਨੂੰ ਅੰਦਰਲੇ ਐਜ ਤੋਂ ਥੋੜਾ ਜਿਹਾ ਉੱਪਰ ਕਰਕੇ ਹਾਸਲ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਇਸ ਨੂੰ ਸਰਕੂਲਰ ਟਰੈਕ ਦੀ ਬੈਂਕਿੰਗ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਸਰਕੂਲਰ ਟਰੈਕ ਦੀ ਬੈਂਕਿੰਗ ਬਾਰੇ ਹੋਰ ਜਾਣਨ ਦੇ ਲਈ ਆਓ ਸਰਕੂਲਰ ਟਰੈਕ ਦੀ ਬੈਂਕਿੰਗ ਬਾਰੇ ਕੁਝ ਹੋਰ ਜਾਣਕਾਰੀ ਹਾਸਲ ਕਰੀਏ। For banking, one side of the road is elevated from the horizontal like an incline or wedge. In this case, the component of normal force in horizontal direction provides the centripetal force as required for the motion along the curved path. On the other hand, component of normal force in vertical direction balances the weight of the vehicle. It is clear that magnitude of normal reaction between road and vehicle is greater than the weight of the vehicle. Consider a car of weight mg moving around a curved path of radius r with linear speed v on a road banked through some angle. Let theta be the angle through which the road is banked. If OA is the banked road and OX is a horizontal line, then angle AOX is equal to theta, is called the angle of banking. The car is under the action of two forces. The first one is the weight mg acting vertically downward, in other words, perpendicular to the horizontal line OX. The second one is the reaction R of the ground to the vehicle acting along the normal to the banked road OA in the upward direction. The vertical component R cos theta of normal reaction R will balance the weight of the vehicle, and the horizontal component R sin theta will provide the necessary centripetal force to the vehicle. Thus, R cos theta is equal to mg is named as equation 1. And r sin theta equal to mv square upon r is named as equation 2. For finding the value of the angle of banking, we divide equation 2 by equation 1 and get r sin theta upon r cos theta equal to mv square upon r divided by mg. That gives tan theta equal to v square by rg, which gives us the value of angle of banking theta equal to tan inverse v square by rg. This equation gives the angle of banking for a speed v and a curved track of radius r. An important point to be understood here is that the angle of banking or the speed of the vehicle has been calculated by ignoring the contribution of friction between tires of the vehicle and the road to the required centripetal force. The value of V deduced here is sometimes called as optimum speed of the vehicle. Actually, vehicles can move much faster than the calculated optimum speed. Remember, we did not consider the role of friction while calculating the optimum speed. Though we all know there has to be friction between the tires of vehicle and the road. we will now learn to find out the maximum permissible speed of a vehicle in accordance with friction. Consider a car of weight mg moving round a curved path of radius r with linear speed v on a road banked through some angle. If theta be the angle through which the road is banked, if OA be the banked road and OX the horizontal line, then angle AOX equal to theta is called the angle of banking. The friction between the road and the tires of the vehicle also contribute to the required centripetal force. In other words, as the vehicle moves along the circular banked road OA, force of friction between road and the tires can be written as F equal to mu r, acts in the direction of AO. This force of friction is resolved into two components, one in the vertically downward direction as mu r sin theta and the other along horizontal in the inward direction as mu r cos theta. You know that there can be no motion of the car along vertical. The total normal reaction on the car balances its weight. Thus, r cos theta is equal to mg plus mu r sin theta as equation 1. If V max be the maximum permissible speed of the vehicle, then the centripetal force is provided by the components r sin theta and mu mg cos theta. In other words, r sin theta plus mu r cos theta is equal to m V max square by r, representing equation 2. From equation 1, we have mg equal to r cos theta minus mu r sin theta. Simplifying this equation, we get mg is equal to r cos theta into whole of 1 minus mu tan theta. Let this be equation 3. Equation 2 can be rewritten as m V max square by r equal to r sin theta plus mu r cos theta. On simplification, we get m V max square by r is equal to r cos theta into whole of mu plus tan theta, which we will name as equation 4. Now, for getting the maximum speed by which the vehicle can easily turn on the curved road with some angle of banking, dividing equation 4 by equation 3, we get m V max square by r divided by mg equal to r cos theta into whole of mu plus tan theta by r cos theta into whole of 1 minus mu tan theta. Solving this gives us V max square upon rg is equal to mu plus tan theta by 1 minus mu tan theta. On simplifying again, we get V max is equal to under root rg into whole of mu plus tan theta by 1 minus mu tan theta, representing equation 5. It is obvious that maximum speed corresponds to limiting friction that acts in the downward direction. The equation 5 gives the maximum permissible speed for a vehicle on a banked road. ਤੁਸੀਂ ਇਹ ਵੇਖਿਆ ਹੀ ਹੋਵੇਗਾ ਕਿ ਇੱਕ ਸਾਈਕਲਿਸਟ ਸਰਕੂਲਰ ਪਾਥ ਵਿੱਚ ਚੱਲਣ ਲਈ ਸੈਂਟਰ ਵੱਲ ਝੁਕਦਾ ਹੈ। ਕਾਰ ਦੇ ਹੀ ਵਾਂਗ ਇੱਕ ਸਾਈਕਲ ਦਾ ਚੱਲਣਾ ਵੀ ਟਾਇਰਾਂ ਅਤੇ ਸੜਕ ਦਰਮਿਆਨ ਫ੍ਰਿਕਸ਼ਨ ਤੇ ਨਿਰਭਰ ਹੁੰਦਾ ਹੈ। ਪਰ ਸਾਈਕਲਿਸਟ ਨੂੰ ਸਪੀਡ ਦੀ ਲਿਮਿਟ ਵਿੱਚ ਰਹਿਣਾ ਹੁੰਦਾ ਹੈ। ਸਾਈਕਲ ਦੇ ਪਹੀਏ ਦਾ ਕੰਟੈਕਟ ਸਰਫੇਸ ਛੋਟਾ ਹੋਣ ਕਰਕੇ ਫ੍ਰਿਕਸ਼ਨ ਸਫੀਸ਼ੀਐਂਟ ਨਹੀਂ ਹੁੰਦੀ। ਦਰਅਸਲ ਸਾਈਕਲਿਸਟ ਦੀ ਬੈਂਡਿੰਗ ਬੈਂਕਿੰਗ ਆਫ ਰੋਡਸ ਦਾ ਹੀ ਆਲਟਰਨੇਟਿਵ ਹੈ। ਸਾਈਕਲਿਸਟ ਸਰਕੂਲਰ ਪਾਥ ਤੇ ਸੈਂਟਰ ਵੱਲ ਜਾਂਦਿਆਂ ਉਨੀ ਸਪੀਡ ਵਧਾਉਂਦਾ ਹੈ ਜਿਸ ਨਾਲ ਉਹ ਫਿਸਲ ਨਾ ਜਾਵੇ। ਇੱਥੇ ਬੈਂਡਿੰਗ ਦਾ ਮੁੱਖ ਉਦੇਸ਼ ਨਾਰਮਲ ਫੋਰਸ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਅਤੇ ਮੈਗਨੀਟਿਊਡ ਨੂੰ ਬਦਲਣਾ ਹੈ ਤਾਂ ਕਿ ਨਾਰਮਲ ਫੋਰਸ ਦਾ ਹੌਰੀਜ਼ੌਂਟਲ ਕੰਪੋਨੈਂਟ ਰਿਕੁਆਇਰਡ ਸੈਂਟਰੀਪੀਟਲ ਫੋਰਸ ਪ੍ਰੋਵਾਈਡ ਕਰ ਸਕੇ ਅਤੇ ਇਸ ਦਾ ਵਰਟੀਕਲ ਕੰਪੋਨੈਂਟ ਸਾਈਕਲ ਐਂਡ ਸਾਈਕਲਿਸਟ ਦੇ ਬੋਡੀ ਸਿਸਟਮ ਨੂੰ ਬੈਲੈਂਸ ਕਰ ਸਕੇ। We consider a cyclist of weight mg taking a turn around a circular path of radius r with velocity v. In order to provide the necessary centripetal force, the cyclist leans through angle theta inwards. During motion, the cyclist is under the action of two forces, the weight mg acting vertically downward at the center of gravity of the cycle and the cyclist, and the reaction r of the ground on the cyclist. It will act along a line making angle theta with the vertical. The vertical component r cos theta of the normal reaction r will balance the weight of the cyclist, while the horizontal component r sin theta will provide the necessary centripetal force to the cyclist. Thus, r cos theta is equal to mg represented as equation 1 and r sin theta is equal to mv square by r represented as equation 2. Dividing equation 2 by equation 1, we get r sin theta upon r cos theta is equal to mv square by r divided by mg, which gives the value of angle of bending of a cyclist in terms of tan theta as tan theta is equal to v square by rg, or theta is equal to tan inverse v square by rg. This equation gives the angle through which the cyclist bends towards the center of the curved road, so as the cyclist provides himself the necessary centripetal force on a horizontal track while going around a curved path. We may finally conclude that the angle through which the cyclist should bend will have to be greater if the radius of the curve is small, or the curve is sharper, and also if the velocity of the cyclist is large. Can you now justify why an ice skater or an aeroplane or any other moving object for that matter has to bend inwards while taking a turn? I have finished with what I was supposed to teach you for today. Let us summarize the important points learned so far. Centrifugal force is the outward radial force experienced by an object when it is in circular motion. The magnitude of the centrifugal force acting on a body of mass m moving with velocity v along a circular path of radius r is given as F equal to mv square by r. The angle of banking of the curved road is theta is equal to tan inverse v square by rg, where the symbols have their usual meaning. This angle depends upon the radius of curvature of the path as well as the speed of the vehicles. The maximum speed with which a banked road can be negotiated is V max is equal to under root rg into whole of mu plus tan theta by 1 minus mu tan theta. The angle through which the cyclist bends towards the center of the curved road so as the cyclist provides himself the necessary centripetal force on a horizontal track while going around a curved path theta is equal to tan inverse v square by rg. We have now come to the end of today's topic. Here is a short question-answer session for you. The first question is, what will be the maximum velocity with which a vehicle can negotiate a turn of radius r safely when the coefficient of friction between the tires and the road is mu? And the answer is, the maximum permissible velocity is given by v equal to under root mu into rg. The next question is, a train moves on an unbanked circular bend of rails. Which rail will wear out faster? The answer is the inner rail will wear out faster. The next question is, does the angle of banking depend upon the mass of the vehicle? The answer is no. The angle of banking does not depend upon the mass of the vehicle. There's another question. In what direction and at what angle will a cyclist lean when going along a curve? The answer is the cyclist has to lean in inward direction of the circular curve. The angle through which the cyclist should lean is given by theta equal to tan inverse V square by Rg. I am confident that you knew the answers to all questions before I told you. I hope you enjoyed the lesson as much as I did and are looking forward to the next class. Thanking you for your attention and see you next time again.